Question 7 gives us a region R which is bounded by the x-axis, the lines y equals to x, y equals to a half, and the curve x is equal to the square root of 2 divided by 1 take 2y squared. From this we need to do two things. Firstly we need to find the exact area of R, and then secondly we need to find the exact volume when R is rotated 4 angles about the x-axis. So what are we actually talking about? Finding an area. This is going to be an integration problem. And finding a volume when R is rotated, well, this is just our volume of revolution. Well, what does our region R look like first and foremost? So I've actually used the computer to sketch the curve, and this is what you get. So let's look at this. This line here, this is our y equals to x graph. This horizontal one is y equals to a half. And this curve here is x equals to the square root of 2 divided by 1 take 2y squared. So the region we're talking about is the region bounded by these three, 1, 2, 3, and the x-axis. So this is our region R. How are we going to find the area of this region R? Well, there's two ways. Firstly, we could do it along the x-axis, right? We could split this up, and this is a half, this is 0, so integrate 0 to half, then integrate half to 2, and then subtract away from root 2 to 2. We could do it along the x-axis. But actually, if you look at this, the integration is much easier if you do it along the y-axis, because you know this is a half, this is 0, and then you just have to take the integral of this function here, subtract away the integral of this function here. So you basically take this area that I'm showing now in green, you take this area minus this area here, and that will give you R. So how do we write it down? Let's get started on question 1 then, right? So our area of R equals to what? It equals to the integral from 0 to a half of x, whatever this function x is, with respect to y, so integrating this function along the y-axis, and then subtract away the integral from 0 to a half of y equals to x, so just y dy. So that's all it is, right? So let's have a go at that. So this is actually the integral from 0 to a half of the square root of 2 divided by 1 take 2y squared dy minus the integral from 0 to a half of y dy. Well, what's this? This is actually the square root of 2, 0 to a half, 1 over the square root of 1 take y root 2 squared dy minus, and I can actually integrate this one very, very easily. This is just going to be a half y squared between 0 and a half. But let's look at this one first. Where have I seen this form before? Where have I seen something in the form 1 minus the square root of 1 take something squared, right? And this integral, well, we know this to be, this is the derivative of sine inverse of x, right? So, and actually, if you think about it, we've already got this root 2 here, which is the derivative of this, which means that that was going to pop out anyway. So actually, what have we got? This one, if I'm to integrate it, I just get straight away sine inverse of y root 2 between 0 and a half minus, and then if I evaluate this one, I get 1 over 8. So that makes this a lot easier. So what do we get? So the first thing we're going to do then is we're going to substitute in our values. So we get sine inverse of, substitute in a half, you get root 2 over 2, or actually if we were to simplify that slightly, put in something that looks a bit more like a trig answer, that's 1 over root 2, minus the inverse sine of 0, right? And then minus 1 over 8. So now it's just a matter of evaluating this. What is the triangle that gives you 1 over root 2? Well, we know our triangles. You can do this on the calculator as well, but they wanted an exact answer. We have a 1, 1, root 2 triangle, right? So that means that this is 45 degrees, if you still think of it like that, or what we call it now, we call it pi upon 4 radians. So this is sine inverse of 1 over root 2 is pi upon 4. Sine inverse of 0, well, sine of 0 is 0, so this is just 0, and then minus 1 over 8. So our final answer is 2 pi take 1 over 8 units squared. And that's the area of R.